Okay, welcome back. This is application of linear functions, video number 13, and we are looking at problem number 109, the homework that was assigned over the weekend. Okay, so this problem was assigned as homework, and we're going to go over this video. So now, reminding you when setting up application of linear functions, there's a key phrase that you guys must remember. Okay, and that phrase is that y depends on x. Okay, y depends on x. Now, remembering that y is called the dependent variable, x is called the independent variable, this phrase allows us to find a point and a slope for this problem very easily. Okay? The first step to solving these application problems is to first draw a graph. So let's go ahead and set up a graph. Okay? And we're going to call this the x-axis, this is the y-axis, but before we do this, we have to figure out what is our x and what is our y. Reminding you guys, application of linear functions, the goal here is to make predictions for what is going to happen in the future. Okay, so we want, notice, let's read this problem and see what it says. It says the Pennsylvania State University had enrollments of 40,571 students in 2000 and 41,289 students in 2004. Okay, assuming the enrollment growth is linear, okay, that's key. Assuming the enrollment growth is linear, okay, that's an assumption that we're making, so we're using what type of function? We're using linear function, okay? Find a linear model that gives the enrollment in terms of the year t, where t equals 0 corresponds to 2000. You use your models to predict the enrollments in 2008, 2010. I want you guys to notice, we want to predict what the enrollments were in 2008 and 2010. Now, before we get to the prediction, we first have to find a point and a slope so that we can graph not only the measurements, but also graph our model, okay? And then figure out, well, by using an equation, figure out what our predictions are. But before we start, a couple things. First off, are the number of students growing or decreasing? If we notice, in 40,000 students in the year 2000, and 41,000 students in 2004, well, there are more students in 2004 than there were in 2000, so we are assuming that the growth, or that there is growth, or that the number of students is increasing, okay? This would be an example of positive correlation, okay? Positive slope, growth, okay? So we do see that there is growth, only 40,000 students in 2000, notice there's 41,000 students in 2004. Okay, so let's get to this phrase, y depends on x. Now, in the last video, I told you guys that you could assume that time is generally the x-axis. Okay, but I think you can hear the dependency in this case. Notice, we have two things. We have students, and we have what? We have year. Okay, in this case, 2000. Let's go ahead and write year. Okay, so two things that we're measuring here. Students and year. So would it make more sense to say that the number of students depends on what year it is, or would it make more sense to say, I'm sorry, I'm backwards. Would it make more sense to say that the year that it is depends on the number of students, or the number of students depends on the year that it is? Hopefully you can hear the dependency that the number of students would depend on what year it is, okay? So again, time is generally our x-axis. Okay, so we're going to call this the year. Okay. Y depends on x. Notice that we said number of students would depend on what year it is. Okay. Generally, everything depends on time. Okay. As time is increasing, the number of students is going up. So the number of students, if we're analyzing this, depends on what year it is. So we're going to call the x-axis year, and we're going to call the y-axis number of students. Reminding you, these are called the units, and we need a variable. Remember that for year, okay, it's a measurement of time. We use variable t. And for number of students, you can choose. Okay, I generally choose a variable that matches the front letter, so let's call this s. Notice that our x-axis is represented by t, and our y-axis is represented by s. We can now set up an ordered pair in terms of our variables. Notice x is t, so we're going to say that this is variable, or ordered pair t, comma, s. Now, we're going to set up a t-table. Okay, remember step one. Step one is to graph. Okay, we will actually delay this. Okay, step two is t-table. Okay, and in our t-table, this is represented by column X, column Y. Notice X is T, so we're going to say that this is T for first column and S for second column. Now let's get the information out of the problem. Okay, notice in the problem they give you time, the year, and they give you the number of students. Do you see an ordered pair? Okay, hopefully you say yes, time and number of students. Our time is the year 2000, number of students is 40,571, so let's write in year 2000, or time was 2000 that year, there were 40,571 students. Okay, now, in 2004, there were 41,289 students. So 2004, there were 41,289 students. But let's read a little further. Notice we don't like to use large values. Again, notice it says here, where t equals 0 corresponds to the year 2000. So it's telling you to use 0 for t when the year is 2000, reminding you of a mapping. If we call 2000 0, what would that make 1999? Okay, hopefully you say that would make 1999 -1. What would that make 1998? Okay, 1998 would be what? -2. Okay, and what would 2001 be? 2001 would be 1. 2002 would be 2. And what about 2010? Okay, hopefully you say that 2010 would be 10. So we're going to map this. 2000 is actually going to be represented by just 0. Okay, 2004, hopefully you say 2004 will be represented by 4. Okay, so now, hopefully you can see that the problem gives us 2 points. Okay, and with these 2 points, we can calculate a slope. Okay, so now, 2 things we need to graph a model. We need a point and we need a slope. Do we have a point? Yes. Pick the point with the smaller values. We're going to pick the point 0, 40,571. Okay. Now our slope is calculated as m equals delta y over delta x using our definition, but in this case, remember, y and x are not being used. We're using s and t, so this is actually written as delta s over delta t, which means, remember, delta means change in, the change in students divided by the change in time. Okay, so the change in students divided by the change in time. Now, down here, we're going to actually calculate this. Okay, so step 1 is to graph, step 2 is t-table, step 3 is find the slope. Okay, so our slope is m equals delta s over delta t, or subtract the number of students, divide this by subtract the year. Okay, so we're going to subtract students, okay, starting with 40,571. Okay, so we have 40,571, subtract 41,289. And notice, we started with the 40,000 for the students. We have to start with 0 for our year. So on our year, we're going to do 0, subtract 4. Now, on top, 40,571 subtract 41,289 is 718, I believe. Negative 718. Let's see. 429, 6, 7. Yeah, 718, and 0 minus 4 is -4. Now, notice that you have 2 negatives. The 2 negatives will cancel and become positive. 718 divided by 4 is 179.5. 179.5. So 179.5. I believe that's correct. Okay, now, let me just double check all the math there so I don't make a mistake. 718, 4, yeah, 4. Okay, now, so what is this saying? Okay, again, we need to interpret the slope. Slope is 179.5. Go ahead and write this over 1, okay? And 179.5 represents the top, remember, is students. The bottom is year, so 179.5 students per 1 year. Now we called this in the last video the average slope. I'm going to explain why in a minute. Average slope. Okay. Notice that if we think in terms of going up, okay, I know we subtract, we end up with negative, but notice that what happened to the number of students. The number of students went from 40,571 to 41,289. That was a difference of 718, meaning that the number of students went up by how much? The number of students went up by 718 students in a total of how many years? Okay, remember, top is students and bottom is year. Okay, numerator students, denominator year. So it went up by 718. The enrollments went up by 718 students in how many years? From 2000 to 2004, in 4 years. Okay, what this means is the average number of students per year increased by 179.5 students every 1 year on average. But my question is, does it always increase this much every year? Can you always expect the enrollments to go up? Or did the enrollments necessarily go up exactly 179.5 students every 1 year? Well, hopefully you say you can't have a half a student. Okay, my question is, could the population of students from 2000 to 2001, could the population of students have gone up by, say, 200 students? Okay, to 40,700 students, and then in 2002 have dropped a little bit, and then in 2003 shot back up a lot more, okay, to level off at that in 2004 they had 41,289 students. Yes. Okay, the population may not have necessarily gone up at a constant exact rate of 179.5 students per year, which actually you can see could not happen. You cannot have a half a student. But this is what we call the average. Okay, even if it shot up in 2001 and then it dropped a little bit in 2002 and then shot up a whole lot more in 2003, okay, the average amount that it went up was 179.5 students per year, the enrollments. Okay, so the enrollments went up on average this much. Okay, this is the trend. Now, so we're going to say that the slope is 179.5, and write your units, students per year. Okay? Now, let's go ahead and graph our data. Okay? Graph the data, 0, 40,571. Okay? I think we have enough space just to do units of 1. Okay? Let's go ahead and leave the origin at 0, 0. So we have to graph the point 0, 40,000. So that means do not go left and right, go up 40,571. Uh-oh, we don't have enough space. Okay, so since we're dealing with a restricted amount of space, we're going to do units of 10,000, 20,000. Okay, so if this is 10,000 and this is 20,000, this means that the next value is 30,000 and the next value is 40,000. I'm going to erase this so we can see. Okay, this is the number of students. So 0, 40,571 students. So we are slightly above 40,000. 0 units to the right, 10,000, 20,000, 30,000, 40,000, and we are just above 40,000. Now, we also graphed the graph at year 4, 41,289. Okay, so at year 4, 1, 2, 3, 4, we are at 41,000, which is even slightly higher, 289. Okay, so notice if we, well, this is very scrunched. Let's see, equals 179.5 students per year. Okay, erase this. Hopefully you can see that the trend is upward. Okay, if we were to graph a line through these 2 points, the slope would be what? The slope would be positive. Now, step 4 is to write an equation. Erase this. Step 4, write the equation. Of the model. Okay, the equation of the model. Now, the equation of the model says, well, we're going to write an equation of a model, a line, okay? We're going to do the easiest equation, or write the easiest equation, which hopefully you say is point slope. Well, we start with y. No, not y. What are our variables here? We have what? S and t. So we're going to start with what? S, then opposite the s value of our point. Okay, the s value, remember this is t, this is s. The s value of our point is 40,571, so minus 40,571 is equal to, now our slope. Slope is 179.5 times quantity, not x, we're using variable t. So t, then opposite the t value, which is what? 0, t minus 0. Okay, so this is the equation of the linear model that we have not even graphed yet. Reminding you, what are these 2 points representing? These 2 points are representing measurement. Okay.
Please pardon the interruption. Well, Mr. Thaxton, Ms. Ahern, Mr. Sherlock, and Mr. Luhoff, please report to Mrs. Brown.
Okay, so these represent measurement. I actually have to cut this video short. I have to go to a meeting, but I will go ahead and put this up. The next, okay, so step 5 will be to graph the model. Okay, the model is a line, okay, that passes through these 2 measurements. Oh, this is a horrible line. A line that passes through these 2 measurements, and notice that our model has a positive slope. Does the line represent the an infinite number of measurements? No. I want to remind you, okay, over here, in 2000 the enrollments were 40,571 students. My question is, in 2001, could there have been a large increase in the number of enrollments? Yes. So in 2001, which is here, okay, this is 1, 2, 3, 4. In 2001, we could have had 50,000 students, and in 2002, it could have shot down. In 2002, it could have shot down to, say, a flat 40,000 students, okay? And in 2003, shot back up to 45,000 or 46,000 students, and then in 2004, we ended up with a population of 41,289. I think this becomes clear. Okay, notice, does our line even pass if there were more measurements? A measurement for 2001, a measurement for 2002, and a measurement for 2003. Does the line even pass through these measurements? No. Each of these points represents a measurement. Okay? The model itself is a theoretical model that we learned in math class. Okay? And this does not represent the measurements. It represents the trend. And the rule is this. We draw the model through the first point and through the last point of our measurements. Okay, so through the first, through the last, and we graph the model. So step 5 is to graph the model, and step 6 is to make predictions. So predict for year 2008. I've got to wrap this up. In 2008, that would be represented by, notice, predicting for 2008, that would be represented by 8, and we're going to plug 8 in for t, and end up with s minus 40,571 is equal to, hopefully with the other video you guys can put all this together, 179.5 times quantity, 8 minus 0, which is just 8. Here, all right, 8 minus 0. We end up with s minus 40,571 is equal to 179.5 times 8. 179.5 times 8 is 800. 8 times 7 is 56, is 1360. 8 times 9 is 72, is 1432, 1436, I believe. 1436, add 40,571, s equals 41,900 and 42,000, no, 41,900, 42,000, 7 students. Okay, 42,000, 7 students. Let me just double check the math on that. There. 179.5 times 8. Yeah, 1436 plus 4571 is 4207. Yes, so we're predicting, based on the trend, that there will be 42,000 students in 2008, and you just have to now predict for 2010. 2010 requires that you put 10 in, okay? 10 in. We end up with S minus 40,000 571. We're putting 10 in for t, okay, equals 179.5 times quantity 10 minus 0, okay, which gives s minus 40,571 is equal to 1,795. And take the negative 40,571, move it to the other side, is plus 40,571. Cross it out. The number of students is equal to 42,200, 366, I believe. 42,366. 66. 16 carry the 1. 12, 13 carry the 1. Yeah, I believe that's right. 42,366 students in 2010. Now, hopefully you can see these predictions make sense. So based on our prediction, the population of the school will continue to increase. Okay, so you're going to, as someone working for the school that is making this prediction, you're going to tell the school that based on a linear model, if the enrollments continue at the rate they are, we can predict or project that the school will surpass 42,000 students in enrollment by year 2008. Okay, so you're able to make a prediction and assure, or we also have measurements for how likely it is that this would actually even happen. But we're going to predict that the number of students are increasing or would surpass 42,000 students by the year 2008. Okay, that concludes this video, and hopefully that helps you guys with tonight's homework.